Determine that population slope is not equal to 0, which means that there is a relationship between commercials, TV commercials, and sales. Now our interest is to find out within what range population slope is going to fall. We determined that it's not 0, but now we like to find out to get some idea how much it is. Like we know sample slope is 5, but how much is population slope? So for that, we are going to do confidence interval estimation. Confidence interval for population slope. Now, I mean, it says 95%, but you can have 90%, you can have 99%, but the most commonly used confidence interval is 95%. Now, nothing is new over here. So if you go back to what we did in confidence interval estimation earlier, okay, so when we are doing it for mean, it was x bar plus minus t. It was like this. Now over here, x bar is replaced by b, okay, small b, and this is replaced by b. That's all, okay. I mean, nothing new is coming. The only thing is notation is changing. So instead of sample mean, you are putting over here sample slope. Instead of standard deviation of standard deviation of sample mean, you are putting over here standard deviation of sample slope. Now, so over here, like if you are looking for 95% confidence level, if you are looking for 95% confidence level, this is what 95% confidence level is. 5% is outside, so 0.025 is here and 0.025 is over here. So you need to find out the t-value with 3 degrees of freedom and 0.025. We just cite the t-value is 3.182. Let me just show it to you again. 3 degrees of freedom and 0.025, t-value is 3.182. So if you're looking at 95% confidence level, your t-value is going to be 3.182. Now, I know what my sample slope is. My t-value is 3.182. My standard deviation of sample slope is 1.08, and the answer is 1.56 to 8.44. With 95% confidence, I can say that population slope is between 1.56 to 8.44. With 95% confidence, I can say that population slope is between 1.56 to 8.44. Tell me, if your conclusion was, when you were doing hypothesis testing, and you concluded that population slope is 0. You concluded that population slope is 0. Then what could be this interval? What could be this interval? I'm talking about the interval. If your conclusion is that population slope is 0, let's say this number is 4.63 is 2.8 or whatever. Conclusion is population slope is 0. Or we cannot say that population slope is not 0. It could be 0. So if it could be 0, then what your interval will be? Very simple. Is there any 0 in between over here? If based on hypothesis testing your conclusion is population slope might be 0, then your interval should include 0. So maybe it might be minus 1.56 to 8.44. There is 0 in between. If hypothesis testing say reject, then interval 1 be having 0. If hypothesis testing results in acceptance, then interval will be having a 0 in between. So we can come to the same conclusion just by making the interval. So if I make the interval, my conclusion is going to be population slope is not 0 with 95% confidence. And it falls between 1.6 to 8.44. Now, you can also do the hypothesis testing using F-test. F-test is simply the ratio of two variances. So again, B1 is equal to 0, B1 is not equal to 0. And what are the two variances? Okay, MSR is simply SSR divided by what? Tell me. Divided by number of independent variables. And MSE is SSE divided by n minus number of variables. So now, how do you get MSR? SSR is it's a measure of it's a measure of dispersion around mean, or it is some of SSR is a measure of like the proportion of variation explained. Now over here SSR, if I like to find out MSR. So MSR is simply SSR divided by number of independent variables. So look over here. Where is that? See over here 100. When I look at my SSR, SSR is 100 divided by 1 is 100. Now the denominator is MSE. MSE is just like variance. Variance around regression relationship. Now how do you get variance? It is SSE divided by n minus number of variables, or in this case n minus 2. Okay. So I'm going to take 14 divided by 3. Okay. 5 minus 2 is 3. Okay. So that is going to give me 4.667. Okay. And the answer is 21.43. Yes.
What's the 100 being divided by 1 again? Where did you get the 1?
100 divided by number of independent variables. So these are the two measures of variance. You just took a ratio of those two, and it is 21.43. If you recall from the last class, that F-test, we are solving it as an upper tail test. We can solve it as a lower and upper both. We can have a two-tail, but it becomes it becomes time consuming. You can very easily solve using upper tail test. So what I'm going to do over here is, I am solving it as upper tail test. So here is your F distribution. This is acceptential. Now, so what you are going to do over here is, because it's a two-tail test. It's a two-tail test, so which means in each tail there has to be 2.5% of the area. Alpha is 0.05 or 5%. So, but if it's a two-tail test, 2.5% each, which means 2.5% is going to be the upper tail. So using 2.5%, and for F test, you need degrees of freedom for the numerator and degrees of freedom for the denominator. For MSR, which is the numerator, how many degrees of freedom you have? For MSE, which is denominator, how many degrees of freedom you have? Over here you have 1 degree of freedom, and over you have n minus 2, which is 3 degrees of freedom. So using 1 and 3 degrees of freedom, you are going to be finding out your F value. So, let me just show you. So 1 and 0.025 here 17.44. 17.44. So at the intersection of 1 degree of freedom for the numerator and 3 degrees of freedom for the denominator, and your area in the upper tail is 2.5%, lower tail is 2.5%, so 2.5% we are taking, so the answer is 17.44. So I'm just going to put it down, 17.44. Over here. Now, my F observed is 21.43. So this is your critical value, F critical. F 0.025, 1 and 3 degrees of freedom. So this is the typical way you write. You first put your level of significance, and the second number is going to be degrees of freedom for the numerator, and this third is going to be degrees of freedom for the denominator. So that is 17.44. Now, my F observed, so this F critical, which is splitting your distribution into acceptance and rejection, your F observed is going to be 21.43. Now what's the p-value? We won't be able to get precise answer, but we can have some approximate answer, and that you can just see over here. So 1 and 3 degrees of freedom. 1 and 3 degrees of freedom. Try to look at 21.43. So 5.54, 10.13, 17.44, 34.12. Above 34.12, you have 1% area. Above 17.44, you have 2.5% area. So I can say that above 21.43, you have less than 2.5% area. So p-value is less than 0.45. You don't have a precise answer using the table, okay? I mean, our answer is p-value is less than 0.45. Since it is less than alpha of 0.025, we are using half the alpha. P-value is less than that, you reject HO. Reject HO if p-value is less than alpha. You got it fine?
In yesterday's class, we said we have to put the bigger number in the numerator and the smaller number in the
So this is going to be bigger.
It will always be bigger. The MSR will be.
Rejecting HO, B1 is equal to 0, and conclude that the relation between X and Y is significant and does not enable us to calculate the cause and effect relation present between X and Y. Just because we are able to reject HO and demonstrate statistical significance, it doesn't enable us to calculate that there is a linear relationship between X and Y. Now look at this. A stock market performance over here and the rainfall in Thailand. So today, let's say Dow jumped by 300 points and it's raining in Thailand. If you do the computation, it is very, I shouldn't say very likely, okay? It is going to be, there is going to be slope. There is going to be value of slope. It is going to be very small, but it's going to be non-zero. It is going to be non-zero. It is not going to be a large number, but it's going to be a very small number. Okay. It's going to be less. It's going to be something other than zero. Can we conclude that there is a relationship? We cannot. We cannot conclude that how Dow is going to perform over here today has to do with whether it's raining in Thailand or not. So that's what we want to be careful about, okay? So just by looking at the slope which is non-zero, you should not be concluding that there is a relationship. You should be looking at what variables we are talking about. Guys, we are very slow. Okay. Extremely slow. Let's do, I'll come to that later, but I just want to go into something else. Okay. What I like to do is go into files, in Excel, go into file in Excel. Can you do that? Go into options. You want me to go back? I can go back. So open Excel. Don't worry about this thing over here. Just go into a Excel, file, more, options, are you in options? Add-ins. Click on add-ins. Analysis tool pack. Can you see that? Go and then highlight these. I mean, don't have to highlight all of them, but if you're not sure, just highlight everything. It doesn't harm you. And then, okay. Show, please. Show. And then when I click on data, I see this thing over here. Data analysis and solver. Solver is for people who are going to be writing MGOC 10 exam, right? Remember you guys, did you use solver? Optimization. We need data analysis. We need this. So over here you have so many different things which you can do. Okay. Analysis of variance, correlation, covariance, descriptive statistics, exponential smoothing, moving averages, regression, all these things. Our interest is regression. Are you following me? You're following me? Okay, our interest is regression. So I am on this chart now, this thing. So what I'm doing, I'm just showing you how to get regression output. So it says over here input by range. This is your Y variable. We are looking at the auto sales example, okay? This is your number of cars sold, dependent variable. Input X range, this is your independent variable, number of TVX. Oh, sorry. Sorry guys. That's too quick. So this is number of cars sold. And then the next one is number of TVX. Over here? Yeah, sure. So over here, you enter the TVX, data on TVX, here you enter the data on car sold. And I mean the first row over here is the names. So make sure you click on labels. Now, it is going to, it is going to give you, I want confidence intervals also. The default is 95%. But if you want 95 and 99, okay, you can have 99, just change to 99. Output range, okay, sorry. New worksheet. And residual just is different between Y and Y hat. A standardized residual, it is just like your Z value. Okay, so and here is residual is the error, is the plot of residual. And here is line fit plot. Okay. So your data is there and you're fitting a line. Okay. Now in our case the data is only 5, so it is not that exciting. Okay, but if there is a lot of data, then you can see the benefit of line fit plot. Okay. And we can also have normal probability plot. So I mean you can have all kinds of things, okay? But it will just become a lot more cumbersome, okay? So I'm just going to run it now. See the magic? You have the output. Okay. Now, so this I just showed you, and what I'm going to do is, I just showed you how to get it, okay? But I'm going to go back to my original one because I cleaned it, okay? So, but it's exactly the same. So you have the same output, you got it? So here is your data. Now multiple R square, adjusted R square, standard error, observations, okay. And then you have over here regression, residual, total, intercept, all that. Now, have you seen these numbers anywhere? Multiple R is just like coefficient correlation. We did manual calculation, we did it. You can check it. R square is your coefficient determination. We did it. Okay, 0.8772. You should have it. We did manual calculation. SSR over SST. We'll talk about adjusted R square when we come to multiple regression. Now, I'll come to the other numbers in a second, okay? This is your SSR. Sum of the squares regression. This is your SSC, sum of the square error or residual. 1 degree of freedom attached to SSR, which is number of independent variables. 3 degrees of freedom attached to SSE, which is how many variables are there? There are 2 variables. Okay, so f n minus 2 is 3. So degrees of freedom for SSR is how many independent variables are there? There is only 1. TV commercials. Degrees of freedom for attached to SSER n minus number of independent variables, number of variables. Okay. So n is 5, number of variables are 2, 1 dependent, 1 independent, so that is 3. This is your SSE. SSE divided by 3 is MSE. MSE is just like variance. Variance around regression relationship. Okay. Variance around regression line, we can also say that for simple regression. Variance around regression line. Okay. Higher this number, more the variation. Okay. Now this is what? This simply y minus y bar from each y value you subtracted the mean value, squared it. And when you sum all of them, it is 114. This is your SST. This is your SST. Can you tell me, when I take SST and divide by 4, what do I get? What do you call that? SST divided by 4. What do you call that thing? MST, but what is this MST? SST divided by n minus 1, right? Is MST. What? Oh, sorry.
Standard deviation of
This is this is what is this? This is your variance. This is your variance. I mean, how do you get variance? From each value, you subtract the mean value, square it, sum all of them, and then divide by n minus 1. So if you take 114 divided by 4, it is variance around mean. Now, so this is it, and so this is your SSR, and I divide it by 1, so I have MSR. This is my MSE, and this over here is SST divided by, so this is my SST, and if I divide SST by 4, I'm going to be having MST, which is simply the variance around mean. Now, this R squared, so this is this 114 over here. Is the sum of is total sum of square? Like you took the differences with mean and added and squared them and add all those. And this over here, of the total sum of square, how much you are able to get rid of by using the regression line. So when I take 100 divide by 114, when I take 100 divide by 114, I'm going to get of the total variation what percentage I was able to eliminate by having regression relationship. Or in other words, I can say what percentage what percent of sales, maybe I should just use it. So let's just do this. 100 over 114 is 0.8772. So I can say that 87.72% of the variation in sales is explained by regression relationship with commercials. So when you take this divided by this, you have 87.72. Now, so listen to me carefully. 87.72% of the variation in sales is explained by regression relationship with commercials. Now, is this thing over here 100? Is this thing over here 100? Is the variance? Answer is no. It is just the numerator in the variance formula. What is that? That is simply this thing is simply the numerator in the variance formula. You need something in the denominator also. The answer's denominator is 1. That's fine. I mean, it could be 2, it could be 3, it could be whatever. Okay. Now over here is this SST. SST is what? Is this, okay, summation yi minus y bar square. Is this a variance? It is just the numerator in the variance formula. So what I'm doing over here is, I am taking numerator in the variance formula, I am taking numerator in the variance formula because I'm assuming that these denominators are same. Right? I'm comparing the variance, I'm finding out, like I'm looking at the total variation, what percentage is explained by regression relationship. So what I did is, I just took this divided by that. Just the numerator divided by that. Is it correct? I'm just taking numerator over here and numerator over here. How about these? They are different numbers. This is 1, this is 3. But what happened over here is we are assuming, okay, that the denominator is same. Okay, so I'll come to that later on. Okay, and that is adjusted R square. Now over here, can you tell me what was your F value? F value is over here, 21.43, which is just MSR over MSC. Remember that? We did it manually. MSR over MSC is F value. This is your MSC, remember, 4.627, can you find it? And when I find the square root of that, 2.16, standard error of estimate. This is also called a standard error of estimate. 2.16. It's the measure of variation around regression line. Intercept, any question about this? And there are 5 observations, okay? Intercept is 10, slope is 5. Can you tell me what was the standard deviation of sample slope? We did it, we calculated it. You have to look at your notes. What was the standard deviation of sample slope? Just go back few pages in your PowerPoint slides. We did it manually. See here. I wrote it down. 1.08. Where do you see it? You see it over here. Okay, I'll bring this on both sides. You see it over here, 1.63. Sorry, 1.08. And we see the t value, 4.63. Now the nice thing about Excel is that if you're using the tables, we will be getting just an approximate p value is less than this or p value is more than this, something like that. But here you can get exact p value. So if your t value is 4.63, your p value is going to be 0.019. So we have exact answer because computer is solving it for you, okay? So this is your p value. Is it less than your alpha? It was alpha over to 0.025, 2.5%. Okay, so it's less than that, you're going to reject it. P value is less than half of the p value is half, okay? Is less than half of the alpha. Because it's two-tailed test. Now, do you remember seeing this? 1.562 and 8.437? We made 95% confidence interval. And this is the answer. You don't see 0 in between. Also, no, this is only 95. I asked for 99 also, so let me just show you the 99. So when you're looking at the regression box, if you pick over there, if you click on 99, you'll be getting both 99 and 95. 95 is default, but it will give you 99% interval also. So this is your 99% interval. But the thing which you see over here is, if you want to be 99% confident, then as far as the interval, it goes from minus 1.3089 to 11.3089. And that shows you a problem, okay? That the more confident you want to be, the wider the interval is going to be. So based at 95% confidence, we are saying that population slope is not equal to 0. But at 99% confidence, we cannot say that. You guys are okay with that? I'll just go back to actually, that one is nicer than the other one. So here is a look over here. These are your residuals. Y minus y hat. Difference between actual value and the estimated value. And I did it in the class. These are squared values, okay? But if I ignore the squares, so this 1, 1, 2, 2, 2. So we did it in the class. Then I squared them. Okay, so that's why you're seeing this 4, 4, 4 over here. but this is actually minus 2, okay, and this is 2 and 2, okay, 2 on square. So we did in the class, so these are your residuals, y minus yn. And these are, like this is helpful for you to figure out if there are any outliers or if the distribution is normal or not. Can you tell me, in normal distribution, if a distribution is normal, 95% of the values are going to be within how many standard deviations of the mean? 2. That's what you see over here when you look at this. Okay, I mean distribution. You actually see this distribution is more condensed. So almost all the values are almost within one standard deviation. In normal distribution, at least 95%, okay, at least 68%, at least 99%. Over here, all the values, so this is, you can think about it as Z value, okay? So there is no reason for us to say that this distribution might not be normal. You guys are okay? Now the other thing which you see over here is, like, it's this is numbers of cars sold. Number of cars sold over here. I mean, here are two values, one value and two values, right? And this circle, the square which you see over here is like a straight line. So, I mean, here is a straight line you going, okay, and here are the actual values. So this is a line fit plot. Okay, it's a line fit plot, and we can see over here, like, the values are very close to this line fit plot. I mean, it's not that it is over here or this thing is over there. I mean, all the values are, I mean, the line is pretty good. And here are the here is the residual plot, okay. And I mean, do you see any pattern in these residuals? 5 values, any pattern do you see? There seems to be randomly dispersed around 0. Okay. And that's what we expect, okay? So, of course, the data is very small, okay. But given that data, still it seems to us that like the residuals are randomly dispersed, so it doesn't seem that there is nothing left out, or it doesn't seem that there is any systematic error, okay, which we still need to eliminate. It doesn't look like that. Any questions about this thing? You guys are okay? Now, so we developed our simple regression equation. So, next month you are going to be having 3 ads. Next month you are going to be having 3 ads. So are your car sales going to be 25? If next month you have 3 ads, are your car sales going to be 25? We cannot say that. I mean, they might be 17, they might be 18, they might be 19, they could be 26, they could be any of those numbers. your sample result is not going to be exactly equal to the population. So again, same example which I was repeating yesterday, mean age of the students in this class is, let's say, 26. If I take a sample of 10 students, do you think sample mean is going to be 26? It could be more, it could be less. Okay. So that's why we make interval estimates. So that's what we're going to do over here. A confidence interval is an interval estimate of the mean value of y for a given value of x. A prediction interval is used whenever we want to predict an individual value of y for a new observation corresponding to a given value of x. Okay. So here I'm going to explain to you both of these in a second. Okay. So confidence interval estimate of mean value of y. So this is what you are going to do over here. And I mean, of course, you are allowed to bring a crib sheet, so you can write down this formula on a crib sheet, and prediction interval of y star. Okay, and that's what you have over here. I'm going to explain you these in a second. Okay. Now, so what's the difference between confidence interval and prediction interval? Over here, just check something. This is your population regression line, or I think you are using what? You are using E, or what will you be using? Can you just check at the beginning? I was using mu or E. E. Want to use practically the same thing. There are, so let's say you put 3 advertisements. You collected data on all the time when you have 3 advertisements, and these were your sales. And this is the mean value. I am predicting this. This is your sample regression line. I am using this value. If I use my sample regression line, when there are 3 advertisements, this is going to be car sales. Mean car sales, okay? But I am predicting this one. If you have 3 advertisements, the mean cars, if you have 3 advertisements, you collect the data on all the time when you have 3 advertisements. These are your sales, and the mean is this. But if I just take a sample if I just take a sample, let's say my sales based on sample are going to be over here. So I'm using this to predict that. I'm using this to predict that. Now what if it's just next month I'm going to have 3 advertisements? My sales could be this, it could be any of these numbers. If I keep placing 3 advertisements every month, on average my sales are going to be these. But if I just put 3 ads next month, my sales could be this or this or this or this or this or this, anything. In which case you have more error? When you are predicting for single month or when you are predicting for average?
Single month.
So if you are predicting for average, this is the error, right? From here to here is the error. But if you are predicting for just 1 month, when you have 3 advertisements, it could be anywhere. So the point over here is, I mean, like when you are predicting for single month, there is going to be a lot more error, more dispersion than when you are predicting for multiple months. Okay, we are looking at average only. Now, so that's why. Sorry. So here is. So this is your standard deviation when you are making confidence interval estimate for mean sales. And this is your standard deviation when you make confidence interval estimate for just a single month. Okay. Now, so t value is same, but this is your standard deviation and this is your standard deviation. In which case, the standard deviation is going to be bigger. Where is the standard deviation, bigger standard deviation, here or here? Which one is bigger?
The second one.
Second one, okay, because there are a greater chance of making an error. You are only predicting for a single month. Single month could be anywhere. If 3 TV ads are run prior to the sale, we expect the mean number of cars sold to be 25. I mean, this is, we are using regression. We are planning to run 3 ads next month, and we expect that we will be selling 25 cars. Are you really going to sell 25 cars? This is just a point estimate. They could be more, they could be less. So we have to make interval estimates. And those interval estimates are of 2 types. If you keep putting 3 ads, if you keep putting 3 ads every month for many months, okay. If you keep putting 3 ads every month for many months, what will be your average sales per month? Or over here we are looking at what will be your standard deviation. So standard deviation you are going to measure like this. So that is going to be 1.4491 in this case. But if you put 3 ads next month, your standard deviation is going to be much bigger. Okay, and that much you can see over here. Like over here, you have an additional term over here, which is 1. So standard deviation will become much bigger. Now let's just go back to, if you keep putting 3 ads every month, then what will be the confidence interval estimate? And we are looking at 95% confidence interval estimate. Your t value is 3.182. Your standard deviation, when you're making an interval estimate for mean sales volume, is 1.4491, and the answer is 20.39 to 29.61. So with 95% confidence, I can say that if we keep advertising 3 times a month, our sales are going to be anywhere between 20.39 to 29.61 on average. The objective over here is to show you that when you make a prediction for a single month, it is going to be, there's going to be more variation, it is going to be more widespread than when you are making a prediction for mean value. Okay, so let's look at single month. It is going to be, so this is your standard deviation when you're making prediction for single month, and your interval estimate is 16.72 to 33.28. Now, Excel is not going to give you this. Calculation for this is pretty time consuming, okay? So this I just did it for your information, okay? And Minitab gives you, but we are not using Minitab over here, in case it's a statistical package. But the point over here was, I mean, when you are using your sample regression line and you get 25 cars, it doesn't mean that you are going to be selling 25 cars next month. You are going to be selling, I mean, there is going to be range. So bigger the range, more confident you are. But also we have to look at whether I'm predicting sales, mean sales, or whether I'm predicting sales for just 1 month. So that's what we're looking at. I'm not going to be asking any question on this in the exam. So this I just did it for your information, okay? It just second. So this Minitab output, I love Minitab, but I used it when I was a student. It's a very powerful tool, but we are looking over here just Excel. You saw all these outputs. I show you all this. Residual analysis. What is residual? Residual is simply the difference between actual and estimated value, which is error. When you look at the residual plot over here, for each X value, each time you put 3 advertisements, you're going to be having sales. There could be 20, there could be 21, there could be 18. For each X value, there are many Y values. The difference between those Y values and estimated value is the error. Those Y values and estimated value using regression line is error. So here is your X value, and here is the Y value, which is simply the difference between actual and the estimated. Actual and the estimated. When you look at this, I mean, do you see any pattern? I mean, it depends upon how you are looking at it. Okay. I mean, we can say there is nothing because some values are above, some values are below, and they are not too far from 0. But you can also say, look, I mean, it's going like this. It's going like this. So, going like that and then like this. But that is a bit too much of a stretch, okay? And the key thing over here is values are not far from each other, from this 0, and some are above, some are below, okay? How about this one? Any pattern is obvious, yes or no? Any pattern. Can I say as X value goes up, your error goes up? Look, if your X is over here, your error is here. X is here, error is here. As X goes up, the difference between actual and estimated goes up. That is the pattern you see over here. Something is missing. You have to include that. Do you see anything over here? Is it linear? It's not linear. So the linear relationship is not fitting well over here. I mean, it is non-linear. So you have to modify a regression model, make it non-linear. Okay, that will be seen in the next class. we cite earlier on the chart ourselves, okay? So this is a lot of residuals. I showed it to you. We are not looking at all this computation of standardized residual, okay? So we are just going to be picking them up from the Excel output. I think we are. Most of the values should be falling within 2 standard deviation, okay? But if they are outside that, then you should have to look at it. I mean, they are outliers. Do we really need them? Okay. I mean, delete the outlier. Or, so there are two things which you can do. When the values, so let's say there are values falling from very far from 2 standard deviation from 0, okay? Then what you do over here is either you delete that outlier or have lots and lots of more observations. This you just saw. We just saw that. You have the, I showed you Excel, but here is Excel output. Now I'm going to be doing this in the next class. Okay, and this one is. Tell me, in finance, okay, in finance, how do you measure risk? Standard deviation is the measure of total risk, okay? That's how you measure the risk. Now, but if your portfolio is well diversified, which risk is relevant to you? Systematic risk, okay, which is beta. What is beta? Beta is simply a major relationship between your asset return in relation to market. So beta is 2. It means that your asset returns are twice as volatile as market returns. So over here we are doing the calculation beta. Calculation beta, and what you see over here is beta is 0.9497. For this particular asset, okay, the beta is 0.9497, which is almost just like the market. Market, what's the beta for the market? Beta for the market is, what's the beta for the market? 1, right? Okay, so let's start over here and we'll continue in the next class. In the next class, we are going to, basically we are just looking at the Excel outputs. So there will be less manual calculation, more Excel output.